One of Earth's most unique features is the enormous gemstone in our sky we call the Moon. But could the Moon be the reason why we even exist? Ever since we first began realizing how ancient and immense the universe is, we've been asking the question of if we are alone, and if not, where is everybody? Or where did everyone go? All those stars, many like our own, surely had planets too, and our better telescopes of modern times confirm that planets are quite common. Still, those telescopes are not strong enough yet to reveal Earth-like planets. They can only see those planets that are either immense in scale, like Jupiter, or very close to their sun. Virtually every exoplanet we have found is both big and hot. Even the so-called Earth-like planets, often overhyped in science journalism, rarely approximate Earth any better than Venus does for temperature or Neptune does for size. Nonetheless, we tend to assume planets in our size and temperature range are common enough. And we also tend to assume moons around all those planets are common enough too. Lots of planets have them that we can see. Indeed, Jupiter and Saturn both have mini moons and larger ones too, of a size with our own. Only Venus and Mercury are without known moons, so close to our Sun that its gravity would tend to make capturing a satellite harder. Indeed, Earth is the only planet we know of that only has one moon. And while our focus today will be on large moons, the composition of them will also come up, as will whether or not it was captured or made, and if it could matter if a planet had just one moon, not a multiplicity or none. The good news is that detecting larger exomoons is easier than small ones, thus we are not likely to wait too long after we find some more Earth-sized and distant planets to find out how common moons of our size around them are either. The bad news is that as of now we have no confirmed exomoons, and getting that first one is hard not just for size. To spot one has the same issue exoplanets have. It's much easier to do if they are large and near the sun, and capturing a moon near a star is harder. As a loose rule of thumb, we tend to hold that a moon can't be stable in its orbit unless the distance from its planet is at least an order of magnitude less than its distance from the sun. The moon needs to be inside that planet's Hill sphere and stay in it, which is unlikely for a captured asteroid on some elliptical orbit around a planet close to a star. The Hill sphere of a body is the region it dominates gravitationally, and for us extends about 4 times further out than our moon currently is, roughly and non-coincidentally out to about the distance of our L1 and L2 Lagrange points with our Sun. Again, Mercury and Venus do not have moons, and Earth only has one, which we believe was made from a collision, not a capture event. Talk of Earth's second moon is hyperbole and a lack of a more familiar term than quasi-satellite or moonlet or Trojan. Those quasi-moons and other Lagrange point drifters or temporary micromoons are a fascinating topic, but not our topic for today, as they would have no obvious bearing on the Fermi paradox, that big question of where all the aliens are. That tends to be more focused on either how we are unable to see those aliens, because they are far away or hide, or we trick ourselves into not seeing them in plain sight, and all of those are popular in science fiction since aliens make great stories there. And even though many of those variations are popular with scientists too, the bigger tilt tends to be to the idea that we just don't see aliens because they are very rare and distant, and possibly short-lived. That life is harder to create and sustain and nourish into civilizations than we have often assumed, that you have a lot of hurdles to get through, and that most planets get filtered out along the way, either stopped at a given barrier or just slowed down by it. We call these barriers and hurdles filters, and break them into 4 scales and 3 timelines. The timelines are fairly arbitrary but useful. By default it used to be filters and late filters, those filters that came after our current state, like if a civilization can avoid self-obliteration and make space travel practical so as to be big enough and long enough lasting as to be noticeable to other species far away, like us in our SETI program, to become a loud alien, as we say. but I found it convenient to break the other filters into early and middle filters too. Early filters being everything that sets the stage for life coming into existence and getting established, and middle being the path of long-term duration and complexity. So an early filter is if a planet is warm enough for life, and a middle filter is if brains can develop, and a late filter is if nuclear war kills us off. The other end of that is our filter strength: lesser, minor, major, and greater. Lesser filters are those where we're talking about coin flip odds, likely enough to occur but likely enough to get through too. There may be hundreds of smaller filters than this too, that 99% of planets make it through, and those can add up, but these are the first true stumbling blocks. As an example, getting hit by some dwarf planets or a large asteroid big enough to tear your planetary crust off and kill even the tiniest microbe on your planet's surface is a filter. We don't know how likely that is to happen. Probably not too uncommon, since how we think we got our own moon, and we have some strong evidence Venus and Uranus have both gotten thumped hard. And even our own moon has a crater 2,500 kilometers across that, had that been a planet with life on it, would almost certainly have lost all that life, or at a minimum anything bigger than some lucky microbes, which would have reset their evolutionary clock back to presumably at least 1 billion years ago. One day I may need to do a compendium of filters, but there's tons, and even a bunch of coin flip odds filters can quickly lower your odds of advanced life to be less likely than not to arise in a given galaxy. Many are a lot less likely to get through than not, and we call these our minor, major, and great filters. Minor filters, those where the odds are an order of magnitude or two against, 10% or 1% passage rates. Major are those where it's less than 1 in 1,000, maybe to as high as 1 in 1,000,000. Great filters, though, are those truly lottery-winning filters, where all on its own it might be able to move a galaxy from having 1 billion planets with life on them to just one or even none that develop advanced civilizations. These proposed great filters are often amalgamations of multiple related steps too. So for instance, the most basic rare Earth filter is a planet of the right size, at the right distance from its sun for temperature, in a low enough eccentricity orbit to be stable-ish at that temperature, and have decent tectonic activity for geological cycles, and a large liquid metal core to generate a protective magnetic field to retain atmosphere. This is basically your M-class planet minimum entry in Star Trek terms, and the sort of place we could probably terraform to be Earth-like without some of the more extreme measures we've discussed elsewhere. A more stable sun of a certain size often gets suggested as a major filter too, though not a great filter. But right from the outset of modern astronomy and serious discussion of the Fermi paradox, and probably because our moon so dominates our night sky when the sun is down, we've wondered if maybe our moon might be a great filter. This is obviously our main focus for today, and we should explain why people think it might be a filter, what reason it might be needed for life, or reasons, as several have been suggested, and they might all be true. One of the newer ones is simply its method of coming into existence. The proto-Earth is thought to have been struck by a dwarf planet, Theia, not long after it formed, though time is relative here, not long meaning tens of millions of years, which is thousands of times longer than the recorded history of civilization. Earth had a native atmosphere at that time, too, one blown off by that event. You'll hear us talk about how Earth is on its second or third atmosphere, and that this modern one has all this oxygen freely floating around in it because of life forms producing it as a waste gas, and all iron and other material near the surface absorbed all the oxygen they could already. But even before that, when Earth was first forming, we were a big and hot ball of gas, molten hot from the start because of the sheer gravitational energy of formation, and indeed we are still molten hot from that event everywhere but the crust. The inner core of Earth is hotter than the surface of the sun. Thousands of miles of rock and magma makes a good insulator. I should note that we could easily have already had one or more small moons at that point too, or for that matter have had and lost minor moons since. That initial period from a solar nebula to a protostar was a fairly quick era, hundreds of thousands of years, but we had tens of millions more years pass while that protostar continued gathering mass and warming up from that gravitational energy and fusion occurring. Earth is usually dated to have formed 50 million years after the Sun. Both of those are somewhat arbitrary figures, but we generally believe Jupiter to be just a million or so years younger than the Sun and the oldest of the planets. Part of why it could form sooner was that it was beyond the frost line, which is where water ice can exist, 3 to 5 AU out from the Sun, as opposed to liquid surface water like Earth has at just 1 AU, or astronomical unit, from the Sun. It was a lot easier for it to hold on to matter, especially the vastly more abundant lighter elements, and Earth would have been losing those to its own heat and the solar wind and radiation coming off the Sun, but may have still had quite a lot. Whenever Theia hit to form the Moon, the atmosphere present on Earth was gone, but it already wasn't what it would have been in its earliest days. Whatever it was, though, again, vaporized off the surface by that collision, and we should assume the Moon's creation event, assuming we're right about how that happened, permanently altered the atmosphere of Earth, as without that collision we might have had a lot of early remnant atmosphere and ocean left behind from materials that otherwise were blasted away. That collision is thought to have devolatilized the mantle. Volatiles, in the context of planetary science and astronomy, refers to a substance that has a relatively low boiling point and can easily transition between solid, liquid, and gaseous phases at relatively low temperatures. Water, carbon dioxide, methane, ammonia, hydrogen, and nitrogen are examples and are core building blocks of life. They were much more mixed, we think, in the mantle pre-collision, and the collision with Theia brought them up to the surface. As a consequence of that, our oceans were probably salty from the beginning. We used to assume our oceans had been slowly growing saltier as it rained on land and brought those salts down in the river to the oceans. Now we think it was probably fairly salty from the start, and some models say that it actually might have been even saltier in the first half a billion years the oceans were around, possibly 7.5%, thrice what it is now. Incidentally, volatiles are often contrasted with refractory substances, which have high melting and boiling points and are stable at higher temperatures, like rock. These would tend to be at different ratios on planets that had not been mostly formed, then smashed with another planet to store their mix. This is a lot of the oxides in our crust: silicon dioxide, calcium, magnesium, and aluminum oxide, and iron oxides being some of the big ones. Our crust chemistry and ocean chemistry is assumed to be both very vital to the formation of life and very touchy, where even minor tweaks might have made life much harder or impossible to form. We don't know if having twice as much of some element or half as much might have undone the process. Maybe even 1% higher or lower abundance of some given chemical might have derailed life forming and surviving here. Indeed, we do not know that half or twice as much might have made it easier, as Earth is our only example of life, and our knowledge of alien planets and alien life, or even primordial Earth, is pretty limited. We discussed what we do know more in our episode on primordial planets earlier this year, but the Moon was a big factor in that primordial era on Earth. After that collision, there was a vast cloud of debris around Earth, and much blew off into deep space or rained back down on Earth. But within a few centuries, or at most a few thousand years, this process was done, and the Moon was there, and an awful lot closer to Earth than it is now. I've seen figures as low as 20 to 30,000 kilometers, or 12 to 20,000 miles, less than a tenth its modern distance. Because of the nature of how tidal braking forces work, it would have made its way out faster earlier, so 2.2 billion years ago, half the time since the Moon formed, and when the atmosphere had already become more or less its modern form of about 4 to 1 nitrogen to oxygen, the Moon would already have been a lot more than halfway out to its present location, and long since tidally locked to show the same face to Earth. The first eyeball didn't evolve till half a billion years ago, so no one, critter or human, had ever seen the somewhat misnamed dark side of the Moon until the space race, which is dark only in the sense of never rotating into view of Earth. So 4.5 billion years ago the Moon was formed, and over the next few 100 million years we got an atmosphere and some ocean restored from volcanic outgassing, lots of volatiles being released from deeper down. At that point, we think the Late Heavy Bombardment Period began, or LHB. We don't know its duration, but we believe it occurred between 3.8 and 4.1 billion years ago, and may have lasted that whole time. Once we get back to the moon and can begin taking more samples from its ancient craters from that period, we may be able to nail that down better. But even by then, 500 million years since its formation, the moon would have migrated heavily from Earth. Likely the moon had already tidally locked, too. The moon wasn't the only body to migrate during that period. Indeed, it's quite possible Earth hasn't been at 1 AU, or astronomical unit, its whole history, or had the same orbital eccentricity or axial tilt it now has either. Planetary orbits are not quite the eternal and stable things we tend to think of, even if very durable and predictable by human standards. Back to that in a moment. We believe back at the time the moon formed, Earth rotated once every 10 hours. That's slowed by its interactions with the moon, and at the same time, we think it should have slowed to not a 24-hour day, but something more like a 60-hour day. You can imagine how such a change might impact life on Earth, and I think we've already painted why the large moon is at least a fairly significant filter of the Fermi paradox, and we still haven't gotten to the main reasons usually listed, which predate our current theory of the moon's formation. By a billion years ago, Earth's day was more like 20 hours long, and even closer to the modern day length by the time anything crawled out of the ocean or evolved eyeballs to look at the sky. Total solar eclipses would have been a good deal more common back then and more before, and lasted longer at that. Based on how far the moon is from us now and moving away at about 1.5 inches or 38 millimeters a year, simple calculations show Earth having slowed to a 60-hour day even as the moon's orbit, its day and year both, slowed to the modern month. Back when it formed, it would have been orbiting in as little as 7 or 8 hours, not the nearly 700 it takes now. You can probably guess the kind of tides we would have with that frequent a lunar orbit and that proximity, giving the moon hundreds of times its current gravity on Earth. There were no continents back then anyway, or oceans. They would all have been blown into space, but things would have slowed faster because of the absence of seas and sky. Indeed, since the slowing of a planet or moon in its spin by tidal locking is much like a bike wheel slowing when braked by its pad, you can think of seas and sky as lubricant on the wheel, making it harder to brake. Combined with that, we believe in the last couple billion years, the tidal effects from the sun might actually have acted to speed Earth up, as while gravity of the sun and moon both cause a bulge toward them that acts as a brake as it rotates past and gets pulled on, sunlight also causes an atmospheric bulge of the air being heated by expansion. One interesting theory from Norman Murray of the University of Ontario notes that those bulges, much like sound, travel at a certain speed through the air based on the air's density and temperature. You can see this with volcano shock waves. This came into play long ago when the planet was also a bit warmer, and the modern atmosphere had developed a couple billion years back. The sunlight-driven atmospheric thermotide would have been about 10 to 11 hours, and would have resonated with Earth's day length when it got down to around 20 hours. They'd have synced up 1 to 2 for a time, and we still have a resonance in our day with the atmospheric thermotide, which is related to our temperature and atmospheric density and composition. Short form, our sea and sky is likely why we still have a day as short as we have now, which currently gets longer by about 18 microseconds a year, and should be an extra hour long in about 200 million more years. Day length is a very big factor in climate stability too. As awesome as a longer day sounds, it means higher highs and lower lows on the temperature each day, and narrows your regions of habitability on a planet's surface. That wouldn't necessarily mean as much to ocean life, but then ocean-based life has its own problems with the Fermi paradox, with the lack of fire or any chemical processes that are hard to control while inside the substance rightly known as the universal solvent. Good luck trying to do any pottery or metallurgy or food storage or nearly anything while underwater, though we examined if civilizations could arise without fire in its own Fermi paradox episode. I should note that the moon being made from a collision is still simply a theory. but it's a lot firmer than Earth's surface was back in that period, since the alternative is the moon was captured and used to be a dwarf planet. That is possible. Jupiter's Galilean moons probably are captures that used to be dwarf planets, and maybe more to the point, could be true of other larger moons around other Earth-sized planets, but there's a lot of counter-indicators to capture. That also opens doors to problems with large captured icy moons, as one of the reasons Jupiter's space is full of huge amounts of radiation is the big volcanic plume constantly jettisoned from Io, its closest large moon. We discussed that more recently in Colonizing Io, but has the effect of leaving that area full of charged ionized particles far worse than our own very lethal Van Allen belt, and Io is stirred up by its big sibling moons. So multiple large moons might be hazardous for life emerging on planets too, and might contribute to atmospheric stripping. As to what caused the LHB around 4 billion years ago to refill our oceans, assuming it did, the moon isn't the only thing that's migrated over time. As mentioned, we don't even know if Earth was definitely always 1 AU, and I think there's a good chance Jupiter actually formed at 3.5 AU, then moved inward, possibly as close as 1.5 AU, and then back out again to its current 5.2 AU distance. The Grand Tack hypothesis covers this and uses it to explain why Mars is small, given that the protoplanetary disk that Venus and Earth formed from on one side of Mars, and Jupiter and Saturn on the other, should have been relatively homogeneous in its density. We can see a lot of protoplanetary disks around other stars, and they seem to be distributed predictably. Thus, Mars should be a lot bigger given the chunk of disk it would have formed from, and indeed might have been robbed by Jupiter. Of course, we could have had other planetary migration, including ejections, and we had some dwarf planet slam into Earth to form the moon, and we think Venus got whacked at some point too. An number of planets could have been gobbled up by the Sun. We think Saturn also migrated closer to the Sun and faster, and we're guessing it and Jupiter were in a 2-3 resonance for a while. There are a lot of ways a planet can get its orbit messed up, but the main one here is disk migration, which happens either when you're in a formative phase of a planet within a protoplanetary disk, or maybe if a big planet gets shredded to create a new disk. There's also 3 types of disk migration, type 1, 2, and 3, but while the topic might be fun for its own episode, we'll bypass dipping into that further now. We think the late heavy bombardment that returned deep oceans to Earth, or helped volcanoes do it, was likely triggered by a planetary migration that perturbed the Kuiper belt, and after Jupiter and Saturn had migrated to their current locations. Candidates include a 5th gas giant that was ejected from the system, and also the later formation of Uranus and Neptune, which, unlike Jupiter that we think formed first, may have taken a lot longer to reach their current sizes than the other planets, as they were sweeping out a larger and thinner region of space. Indeed, their ability to exist has often been a bit problematic, leading us to wonder if they might have formed closer to the Sun too. So migrating to their current spot could easily have triggered the late heavy bombardment period 4 billion years back. Again, this isn't a video on the role of Jupiter on the Fermi paradox, which is now screaming in my head to write, but we're seeing how we need to avoid thinking of planets and moons as permanent features unchanged by time. Indeed, given that planet means wanderer in Greek and got the name for wandering our night sky relative to the stars, I think it's ironically appropriate to see that flexibility of position being restored to them after the rather mechanistic clockwork view of them we had in the era a few centuries fore and aft Kepler and Newton. They are dynamic systems, and dynamic systems can often be easily perturbed by minor shoves or variants, and that's exactly the sort of feature that you'd expect for a great filter, something where factors being just a little different might have made life or complex life impossible, and maybe be non-obvious too, as like day length, we tend to assume it has a pretty wide bracket, and clearly it did, since the day used to be much shorter. But shorter days means stronger weather and erosion, while longer days means less of both and more sharp weather. Imagine if the Earth did have a 60-hour day. 24-hour days are not a common thing either. We can get that impression because Mars has a day just a bit longer, and basically no moons to speak of, as Phobos and Deimos are barely mountain-sized rocks. However, virtually every rock in the solar system rotates in under 10 hours, or takes a lot longer than a 24-hour day. The gas giants come closest, with Neptune, Uranus, Saturn, and Jupiter at roughly 17, 16, 11, and 10 hours rotation respectively, and that's their rotation period. Uranus got knocked on its side sometime in the past and points its poles along the plane of the Sun, rather than more or less perpendicular to it as most planets do here and elsewhere. So the Sun just spirals around its sky every 16 hours, but stays up for decades and dark on its backside the whole while. It is a planet just built from the name up to be the butt of jokes. Venus is similarly screwed up, with its backward spin and day longer than its year, and Mercury has 3 days for every 2 years in a weird and eccentric elliptical orbit. That's 3 of 8 planets, and we want to throw in Pluto as 9, it would then be 4 out of 9, since it and its primary moon, which is very nearly a double planet, also has a long, long day. So unless our solar system is a bit of a freak, and thus not a mediocre example for the mediocrity or Copernican principle, then normal is not as normal as we probably think, and we should not assume too many planets resemble Earth even where they've got the mass and temperature right. We've seen the role the moon has in that. It also factors into axial tilt, which controls the severity of seasons. It might not take much to push Earth into a snowball Earth scenario, frozen all the way down to the equator. Indeed, we suspect it may have iced over completely on multiple occasions, or to cause desertification to large stretches of land so that only coastal areas could keep decent and hospitable soil. Think of the Sahara or tundra, and think how easily those can move out without a robust ecosystem helping hold the place together. Crazier and less hospitable climates will tend to make for shallower ecosystems, those far more vulnerable to collapse and extinction. We think the moon is also a factor in the axial tilt for Earth. And here we finally start getting to some of the filters involving the moon that predate the collision formation theory. Note I say filters because while the moon is often imagined as a great filter, it's got a lot of ways it factors in that might all stack up but should be discussed separately. I've been trying to cover the newer ones first and in more detail for folks wondering why I haven't mentioned the effects of ocean tides on our ecosystem or tectonic activity, which tend to be the two classic Fermi paradox points for the moon. A lot of times the moon was listed as a great filter simply because it was so big compared to Earth, but there are half a dozen moons in the solar system alone as big or bigger than the moon, probably captured dwarf planets, of which we have a lot more than Pluto even today, but all further out except Ceres. We don't really know how common big moons are by capture or collision formation, either by model or experimental data, as we have not detected an exomoon yet, and the models are very hard to do because they are 3-body or n-body problems, and the 3-body problem is called that for a reason, and not for its relation to dark forest theory. See that episode for discussion of that Fermi paradox idea. As to axial tilt, the moon stabilizes that tilt. Without it, we would likely wobble more, not simply have more or less axial tilt, but a changing one. The direction already changes on a roughly 20,000 year cycle, and other planets have their tilt change. Indeed, just having ice move off the poles, either thinning or thickening, and thus moving mass around from equator to pole, can change our planet's tilt. So it is easy to perturb, and the moon has a stabilizing influence that a smaller moon would not. And multiple moons likely would not benefit that either. We are pretty confident it had a 12-degree tilt about 84 million years back, and probably severe shifts many other times. Prior to finding out about the one 84 million years back, we had thought the Earth's axis had been relatively stable in the recent eon, and it does do a good job snapping back into place, possibly doing major tilts every few million years. This was another popular moon filter, a very stable axis over long times, but one that is probably not valid anymore. I should note that if you're ever not sure how disastrous something like that is, remember we can only even find out it happened by the evidence it left behind in the form of something so disastrous it left fingerprints that survived millions of years. More massive planets generally will have more stable tilts. Mars has a fairly severe change in its axial tilt, for instance, and Jupiter and Saturn fairly minimal. We can easily argue the importance of not having too much tilt to provide stable and mild seasons, but you can also argue that seasonal variation has its value in pushing evolution. Some folks reason that too stable an environment can also cause organisms that get too good at surviving in it, so that mutations and migration tend to have a problem getting a foothold. So axial tilt is probably a modest filter in its own right, and falls under the Moon's wider filter collection, but has some question marks on its role and importance. This is also true of tectonic activity. Earth has a large core of molten metal, and we have to assume the Moon's size and proximity has helped keep that hot and mobile compared to other planets, which might have cooled and have a thicker crust, less tectonic activity, and an ebbing magnetosphere that would let atmospheric stripping occur far faster than now. But we're not too sure what degree the Moon plays in this, and the Sun also causes tidal effects. Probably the Moon's role was vastly stronger in the past since it was closer, but it's still considerable. The thing is, we just don't know how much and in what way. We have only Venus to compare to Earth in size, as it's not much smaller than us. It's not really the spinning core of a planet that causes the magnetosphere, it's the spinning outer core. The tangential velocity is what matters for strength, not the period, so the further out you are, the faster you are actually spinning, and the stronger you are producing a magnetic field. We don't know much about Venus's core, but its magnetosphere is much weaker than Earth's, and we think its outer liquid core is much smaller as a result. There's a lot of question marks there, unfortunately, and the same for geological turnover. You really need to recycle your planet's surface regularly, at least on geological timelines, or else you're going to end up with one big mud ball. Or if the oceans are deep enough, a big ocean planet with no surface land, from it all eroding away. That might be very nice for life in general, a giant planet-wide mud pit, or epipelagic planet, as we discussed before, might be very dense in life, but probably not in technology, and a planet with deeper oceans relies on deep-sea thermal vents to power its ecosystems. This is where we think life on Earth might have begun anyway, but we don't truly see large and robust ecosystems until photosynthesis gets into play. It's also a point against the Moon as a great filter. At the time it was a lead candidate, our lead candidate for the origin of life was in coastal tidal pools, which obviously benefit from a big moon nearby helping cause them. If it was deep-sea thermal vents, then tidal pools might still be important in helping life transition out of the ocean onto land. But given that life didn't transition onto land till 500 million years ago, when the Moon's tidal forces had dropped significantly since its early and proximate days, with stronger gravity and a faster orbit of Earth, I'm not sure that notion holds up well. So too, the Sun does cause tides on Earth itself, as will any star on a planet not tidally locked to it. And these ought to be a lot stronger on orange and red dwarfs, K and M type stars, which make up 9 out of 10 of the stars out there. Still, having two major tidal sources, Sun and Moon, has doubtless created some wider tidal effects, variety, and tidal zones, which might imply multiple moons might have similar effects for planets that had them. Thus, the tidal effects of the Moon on the seas, and life as a result, isn't to be underestimated, but isn't to be overestimated either. We don't really know how much the Moon churns our planet and contributes to volcanic activity or tectonics, but while we don't think Venus has tectonic plates, it does have some decent volcanic activity. It also has an atmosphere 100 times thicker than ours. So we want to be a little careful casually assuming a magnetosphere is all that keeps a planet able to breathe. A lot of other filters offered up by the Moon are even harder to quantify or be certain about, which is part of why it waned strongly as a great filter candidate in recent decades, though I think some of the newer ideas about it that we discussed earlier help it wax back to a greater possible role. It does stabilize our axial tilt and thus our climate stability. It surely has played a role in promoting geological activity such as plate tectonics, which is essential for recycling nutrients and maintaining a habitable environment. We're just not sure how much. We used to stare up at its crater-pocked surface and assume it took a beating for us, acting as a shield, but that's probably not too big a factor. Earth's taken it on the chin repeatedly, our skulls just tend to be covered over by geology and ecology, while the moon shows its pummeled face and has no atmosphere to help burn the rocks up before they strike. We can easily see the importance of the moon to us. It hangs in our planet's history much as it hangs in our night sky. And yet, even if we assume a large moon is necessary for complex life and civilizations, which I'm reluctant to grant, we finally need to discuss how rare such a moon is, where it's basically a dwarf planet, indeed more massive than Pluto is, and arguably a double planet. On the other hand, it's not very rare at all. Jupiter has 4 moons of the dwarf planet scale, 3 of them more massive than our moon, and the 4th, Europa, not much smaller. Saturn's moon Titan is bigger than our moon and actually has an atmosphere thicker than Earth's, and both Europa and Titan have been serious candidates for extraterrestrial life in the solar system. Triton around Neptune isn't much smaller than Europa and still bigger than Pluto or Eris, the lesser-known dwarf planet that is bigger than Pluto itself. Ceres, queen of the asteroid belt, is often called a dwarf planet and was actually deemed a planet for the first century or so after its discovery, which was before Neptune or Pluto got found and not long after Uranus. Ceres is closer to Earth than Jupiter, and while much less massive than our moon, would be easier for a planet to capture and probably could emulate most of the effects we attribute to our moon. It would not be hard to imagine a perturbation scenario that let Earth capture Ceres, or more to the point, some Earth-like planet capture a dwarf planet, even though getting something to the scale of our moon by capture seems a heavier lift, so to speak. Given that we captured Theia, which we think was closer to Mars in size than our moon, so maybe shouldn't even be called a dwarf planet, but just a planet, we can make the case that such captures are not ultra-rare. But we didn't capture Theia, we collided with it. And while we initially thought we might have had the two do a capture and slow spiral down to each other like we imagined with a Roche world, see our Double Planets episode, we now tend to think they did smash right into each other. That Theia formed at our L4 or L5 Lagrange point with the Sun, and slowly spiraled backward toward us until smacking. Indeed, we have some models and evidence that there may be surviving chunks of Theia in our mantle, large low-shear velocity provinces. How rare would that be? Honestly, we really don't know. I've seen models predicted as high as 1 in 10, which would be our minor filter category, the one just over lesser, to those in the 1% or lower range, which would border into major filters. With all respect to the folks who did those various models, because they deserve it, there's also a lot of uncertainty in the odds and setup in them. We really need to come up with more exoplanet and exomoon data, along with protoplanetary disk data, to help us refine them to any degree of certainty. Right now, I don't think we can really conclude moons formed by collisions are hyper-rare, but it could be way less than even 1 in 1,000. And that's hardly going to be uncommon in a galaxy-wide setup, where if 1 in 100 systems had an Earth-mass planet at its Goldilocks zone, and 1 in 1,000 of them got a collision moon of our scale, that's 1 in 100,000 systems, and still means around 1 million twins to the Earth-Moon system in our galaxy alone. And it does not include captures, of which we have some more examples in the solar system, though a lot of the filters we discussed earlier would not apply to a captured rock, like the churning up of volatiles from the mantle or voiding of whatever native sea and sky there was, or the huge shift in day length for that matter. So we probably need to differentiate not just for large moons, but collision moons versus capture moons. We can't really assume that such a collision would inevitably be followed by an ocean-restoring bombardment phase, which in our case was 500 million years later anyway. So you could have a lot of Earth-Moon clones out there that had no seas or sky. The relative size of the moons to the planet probably matter a lot too. Not simply that they are dwarf planet scale, though as we discussed before, life, and land life especially, get very dubious once you get much bigger than Earth, because of possibly having much deeper oceans and shorter mountains. But given that a collision that formed a big moon might rip those off, for a possible replacement by cometary bombardment, that case for bigger planets with life might be better. However, we care about them being bigger mostly because they could more easily capture a large moon, and that's a redundant point if the moon was made by collision. I should also note that it might turn out only planets of at least our mass are big enough to hold an atmosphere for billions of years, but that anything with our mass or greater would begin with too much sea and sky for a planet, and thus only in the case of planets of our size, smashed by a dwarf planet early on, can life-friendly conditions persist. And if true, that's a pretty decent filter, as you'd have a very narrow range of planet mass, temperature, and collision probability. Maybe even great filter scale. You may also need something like our moon close at hand to convince yourself that travel to somewhere else in space is possible, though I doubt it, and in some ways a smaller moon would be easier to reach and settle and utilize. And in the absence of a big moon, a planet might have tons of smaller ones, or a planet might have a big moon and a bunch of smaller ones anyway. The gas giants do, and Pluto does even if it's smaller than us. So many unknowns and unknown unknowns, so that I feel we can say with certainty that our moon was a critical factor in how life on Earth played out, but not that it's a critical factor in life being possible on other planets, or that such moons would be so uncommon as to be great filters of the Fermi paradox. But in the wider rare Earth and rare Sun camp of the early filters, rare moon certainly deserves its place as host of a lot of lesser and minor filters that could add up to make life pretty rare even before the middle and late filters kick in to keep complex and technological life rare or short-lived. Alien civilizations may have sprung up on places with no large moon, or even, as we discussed elsewhere, sprung up on a large moon of a large gas giant. No matter what else though, there's no denying the importance of the moon to us, and the role it will play in helping us get off Earth to visit and settle strange new worlds beyond our own. We've got some show announcements in our schedule coming up in a moment, but first, one of the interesting things about doing a show like this is that you tend to start paying attention to commercials in a different sort of way, and one of those that many often make wild claims that can't be quantified. That seems to come up a lot with shaving. I remember why I switched to a safety razor almost 20 years back, and it was because I was in the army and I had gotten tired of cheap plastic disposables snappy in my field pack, and electrics whose batteries died and always seemed to get gummed up, or tried to rip my hair out. I thought I got a better shave out of a safety razor and certainly saved a ton of money, but it hadn't really occurred to me that this was quantifiable or that there was an optimal method of shaving. Since I started working with Henson Shaving earlier this year, I've changed my mind on that, because instead of sending me lots of buzzwords to throw at my audience, they sent me data and charts and animations explaining how their razor works. No gimmicks or subscriptions or wild claims, just the facts and a very well-made razor. Henson's is into precision and data, no surprise since they manufacture pieces for Mars rover and the space station. They make a quality aluminum razor, not plastic, with a built-in 30-degree angle optimal for shaving and a tight fit for the razor so it doesn't bend and flex too much. The blade extends just 0.0013 inches past the shave plane, less than a human hair, and this simply results in a smoother shave and less skin irritation. I've been using mine for months now and noticed the difference. Way fewer nicks and red bumps from a better razor and a better method. Stop wasting money on disposables and elaborate 5-blade cartridges. One 10-cent blade is all you need if it's held in place by precision engineering like Henson Shaving offers. Try it now at hensonshaving.com/IsaacArthur, and Henson Shaving will throw in a free 100-pack of razor blades if you use the promo code IsaacArthur at checkout. Get a better shave at a fraction of the cost. Go to hensonshaving.com/IsaacArthur. So before we get to our schedule, I wanted to remind everyone that the National Space Society's Space Policy Debates program is offering high school and university students around the world an opportunity to debate the hottest topics in space exploration, utilization, settlement, and governance. If you enjoy debates and are a student or a teacher interested in mentoring them, and want to help explore the cosmos and shape the future, check out the SPUN debates. We were looking at large moons today and will continue that next week as we travel to one of Jupiter's larger moons, Io, to ask how and why we might settle that volcanic moon. Then it'll be time for Sci-Fi Sunday to explore the concept of mushroom-like extraterrestrials and fungal aliens. After that, we'll dive into the topic of ocean habitats on Earth and beyond. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. SFIA's episodes also come out early and ad-free on our streaming service Nebula, like this month's exclusive episode, Caretaker AI and Genus Loci, at go.nebula.tv/isaacarthur. As always, thanks for watching, and have a great week.